Good afternoon, and thank you again for joining us for today's virtual discussion on causal impacts presented by Dr. Dave Sheets. My name is Mike Seaman, and I work in the Graduate Admissions Office at Canisius. Before we get started, I wanted to let you all know today's presentation will be recorded and will be made available after the conclusion of today's virtual discussion. Also, I wanted to encourage you to ask questions throughout the discussion. You can either use the Q&A section or the chat, and we'll be answering them at the conclusion of today's discussion. Now I'd like to turn things over to Dr. Sheets to begin today's virtual discussion. Dr. Sheets, take it away.
Hi, thank you all for attending today. Dr. David Sheets. Please do turn on the chat. If you can give me feedback during the talk, if you have questions that arise that you want to ask, kind of in real time, please use the chat feature. Don't hesitate to do that. I always like to have people responding and asking questions. And you can also use the questions section, and we'll kind of cover those at the end. I'm director of the graduate program in data analytics. We're entering into our third year. We've had a number of students in the first 2 years, and so far it's going well. We're having a good time with it. I'm here to talk really about hypothesis testing and how advanced analytics helps within hypothesis testing, particularly from observational data. So without further ado. So what we're talking about here is using big data methods to learn about customer and internal behavior of your organization and to use that to drive business value. And so we're going to be talking about a couple different types of technology. Some of the examples of this are Google's causal impact models and the nearcasting idea, which is to make short-term economic forecasts in a fairly automated way. And that's the technology we'll be looking at here a little bit. Facebook has a system out called the profit system, which works in a very similar way. It's this near-term economic prediction system, which can be used in the same sort of approach. And then MasterCard has a program out they purchased a company called Advanced Predictive Technologies, APT, and they have a test and learn system that's being picked up by a lot of industries. So it's these are a couple commercial examples of these types of technologies. So for a little roadmap of where we're going today, I'm going to talk a little bit about what is hypothesis testing. It's a fancy word. It's common in scientific circles. I'll show you how you're actually using that in day-to-day life and think about how you can use that in the business world. We'll then talk about what's called a causal impact from observational data. So talk about what all that means, some fancy words there, but that's using your data within your system that you've observed that's not part of a formal experiment to extract information typically that you get in hypothesis testing. And then we'll take a look at a couple examples of causal impact estimations. One on the Volkswagen diesel emission scandal. Volkswagen was assessed an substantial EPA penalty, in fact, a historically large one, over their emissions cheating on diesel engines. And that had an impact on their stock prices, and there's a way to get an estimate of just how large that impact was on VW stock prices. And we'll look a little bit at about New York State, New York City excess mortality in the pandemic era. So this is using kind of raw data about mortality to estimate what the impact of the pandemic was without having to rely on diagnosis or testing. So how do we learn about the world? And so part of what is driving a lot of the work in causal impacts is this question: how do we learn about the world? And I think for humans, we can break this down really into three categories. Observations, we learn by watching things in the world around us. Interventions or experiments, which means we go out and interact with the world and try something, right? And then narratives, right? As humans, we learn a lot from narratives, whether it's a YouTube video or a book or a discussion like this one, right? We hear somebody talking about how the world works and you make use of that in your own life. So those are those general categories here. So learning from data. So there's two real questions here that a lot of people are thinking about at the moment. One is, how do we teach artificial intelligence systems to learn from observational data, right? Humans can do this. How do we abstract that in ways that would let a machine do it, right? When we're starting to talk about learning from observations, we're talking about causes here, right? In statistics, we really measure correlations, right? And that's been the known way of thinking about things. And correlations and causes are not the same thing. And the mathematics of cause is kind of an undeveloped area. There's a lot of fascinating discussions going on right now about how do you make mathematical statements about causes? How do you embed that in mathematics? And a lot of that is tied to thinking about how you make computer systems learn about causes and about how the world works from observational data. But the other side of this is how do we learn from the masses of data that are accumulating now in the electronic world? How do we learn from that, right? How to make use of all these observations? They're not really true experiments in most cases. We'll talk about that distinction in a little bit. But how do we learn from the observational data that all businesses are acquiring now? How do we learn about systems from that? So hypothesis testing. So within the world of science, hypothesis testing has been a strong way of learning about the world. And it works in a very sort of specific way. It's not the only way, right? Science is not the only way to learn about the world. There are a lot of other ways, viewpoints. Science is an effective way, at least in some cases. So hypothesis testing. Basically what we do is we make a claim or a statement and then try to show that it's false. So that seems a little strange. People set out to prove something, and that's not really what happens. You really kind of try to articulate a range of possibilities, right? A set of claims about the world, and then try to show that most of them are false. And that leaves you with a statement that what remains is useful. Not necessarily true, but useful. So that's the way you need to think about things, right? How do I disprove something that leaves me with some inference about what must have been true? So we carry out hypothesis testing on kind of a regular basis. Most of us actually use this in day-to-day life. And so here's a really simple, we don't call it that, right? We say, oh, I'm going to set out to test some hypotheses about what's happening. But a lot of times when we're solving problems, this is exactly what we do. So suppose you wake up at night and you turn on the light by the bed and it doesn't go on, it doesn't turn on, right? You reach up, try and pull the light chain and nothing happens. So how do you figure out why it didn't light, right? This is probably an experience a lot of us have had. So let's think about a list here. So what we're going to try and do is think about causes for why the light didn't turn on, what the hypotheses are, then how we test that hypothesis, and then think about whether the test is an experiment, an observation, or part of a narrative. I'm going to ask you to give me a little bit of feedback quickly on the chat here. What would be some reasons why, when you went to turn on your bedside light, it didn't turn on? And if you can tell me about whether that's a hypothesis, what the hypothesis is and how you might test it. Yep. Good. I see power outage. Yep. If you can tell me again how you might check this. And okay, yeah, there's a good one. And whether you're thinking about an experiment, an observation, or a narrative to do so. So when I say experiment, what I mean is an intervention, right? Because when we do an experiment, we've got to go and influence the world, right? We've got to go and do something to the object and find out whether our interaction with the world has changed things, right? An observation was something we can just look at and see, oh, well, that must be happening. Or a narrative would be, our sort of past history. Probably a lot of the testing that we're going to look at here is based on narratives, actually. I have some ideas about what you do. Okay, I'm seeing a bunch of good ideas there on this, right, about how to get at this. Okay, well, let's take a look. I got a lot of good suggestions there. It's great. If you're still going, keep going. But I'm going to go to my list of these. Find my cursor. So here are some of the things that people come up with a lot. Cause, the power is out, right? So the power went off. So one thing you might do is look at your clock, right? See if the alarm clock is still running, right? I got an LED clock sitting there. It's an ancient one. So if you look at the clock and the clock is out, then you've got some sort of statement of, oh, the power is out, right? And that's an observation, really. The lamp is unplugged. That may be another reason. Or for some reason, maybe I kicked it when I went to bed. I could look at the plug. Again, that's an observation. Maybe the fuse is blown, right? Or the circuit breaker is blown. You could go downstairs and check the circuit breaker. Hopefully check to see if you've got something seriously wrong before you do that. But that's an intervention, right? Changing the fuse would be altering the world. Maybe the wall plug failed, or the bulb is broken, or the switch is broken, right? There are a bunch of things we could do wrong. Yeah, we might be hitting the wrong switch. A bunch of different ways to think about this. And when you think about this, we would be trying things, right? Probably you do something first, like look and see if the clock is running, right? That's an easy one. You don't have to do much, right? If I try to turn the light on, the clock's out. Well, that's the end of things. And then we go through more and more complex sort of results here. And most of the time, it's either an intervention or an observation, right? We can look and see, oh, there's something obviously wrong, or maybe we got to intervene, right? If we replace the bulb and see if a new bulb fixes it, that's an intervention, right? And we kind of work our way through this. And it, as it said, it could be, somebody just mentioned, it could be a multiple of causes, right? That's when things get really ugly, right? If the bulb is broken, it's unplugged and the power is out, and the switch has failed, it's going to be a long night, right? You're going to have a long time to figure out what's going on there. Most often it will be a binary type of cause. There'll be one thing that caused it, hopefully in the near term, but it's possible we've got more. So I'm just really, the point of this exercise to think about is we actually do this, right? This is a common thing in human life. We don't say, oh, I'm going to test the hypothesis, but in fact, that's what we're doing. We probably often check the easy ones first, right? Humans are often kind of lazy, and we check the easy things first, so check and make sure it's plugged in and the clock is running and those types of things you do first, right? And replacing the switch is probably well down the list of things we'd try. As someone noticed, one of our panelists noticed, we might have multiple causes, right? And we think of these as contributing factors, right? We often want to know what we call the impact of one particular factor. So when you think about something like a medical treatment, right? If you're trying to, and a lot of the examples that I'll mention really came out of medical treatment, right? That was a place where the idea of controlled trials and double-blind studies and all this was really developed. That and agriculture, right? Those are the two areas where, as humans, we started to use these techniques a lot. And if you think about it, it sort of makes sense, right? Because if you apply a medical treatment to people, well, it turns out that most of the time when people are sick, they actually get well regardless of what you do, right? About 70% of the time, if you go to the doctor for some sort of treatment, you would have recovered whether you're treated or not. It's a good idea to go to the doctor. I'm not slighting that, but the fact is humans do pretty well. And we all know about things like the placebo effect. If you just go and talk to the doctor and he gives you a sugar pill, you feel better and you think that that's psychologically helped. So we know there's a lot of possibilities with medical treatment. And conversely, if you go in for treatment of one problem, you may have a second problem that, causes, mortality, or causes an adverse outcome that had nothing to do with the treatment, right? So we've all got a lot of that going on in the medical world. And certainly if we're talking about crop fertilizers, you could use this great fertilizer on your field and have drought, right? And so you get a lousy crop, right? Nothing to do with the fertilizer, it's a completely different cause. And more often you get these interactions, right, where it's a combination of a lot of these. And we're often trying to isolate out and say, well, what impact did that medical treatment have? Or what impact did the crop fertilizer have? If we're running an ad campaign, right, what effect did the ad campaign have, right? Because we're trying to sell our product and there's an economic downturn. Well, so everybody's products sell badly, right? And the question is, well, how do we do, what impact did the ad campaign have, given the fact that nobody's products sold well, right? We might have been in even worse shape if we hadn't had the campaign, right? So those are the types of questions we're getting at, is trying to dig in there and say, from those multiple causes, how do we break down and attribute how much contribution there was from each one, at least on an average sense, right? If you look at a lot of people, you could say, well, on average, the medical treatment prolonged their life by 6 months, or, it reduced their chances of getting sick in the next year by 10%, whatever we need to do there. So within hypothesis testing, historically and currently, the gold standard is a randomized control trial. And these are done slightly differently in different fields, right? In medicine, it's often a double-blind trial, so that the people carrying out the treatment don't know whether it's the real drug versus a placebo, because the clinician's attitude influences how the patients do. In a lot of advertising, it might be simpler, right? You don't need to double-blind it. You can divide your customers in half and send one ad to half of them and another ad to the other half, or on the web. There's a continuous shifting, right? It's very easy on the web. If somebody visits a website, that they're going to see slightly different things, they're going to get different ads, and you can track all that. The randomized control trial idea dates back to the 1920s. Statisticians Jerzy Neumann and Ronald Fisher developed a lot of them. They were working a lot in agriculture. And so here's the example that I want to talk about today, and to show you what a randomized control trial looks like, and then talk about some of the other types of alternatives we might use when it's not possible to do that randomized control trial. So here's the situation. Suppose we've got a company and we sell window cleaners, and we want to test whether mail coupons or direct mail ads work better in boosting sales. So that's the statement we've got, and by how much. And so we think the mail ads cost us more to send out. We got to pay postage on them. We got to have paper, and the digital ads are cheaper, right? We send an email campaign out. And so we're only going to use the mail ads if they do a much better job. And so we could say, well, given what the cost of producing that ad is and how much better it worked, we could calculate a kind of an expected gain, right? And decide whether or not it made sense to do a direct mail ad versus email. So we want to know two things. Is one ad tactic better than the other, right? We need to know that. And we'd like to know the causal impact. And so the causal impact means the magnitude of the sales increase due to the shift in the sales or the ad type. So let's suppose that this picture represents our customer base, right? And we've got a customer base that's a mixture of residences, so that's little houses on the left, and businesses on the right. And suppose we've got different paint schemes, right? And so we've got yellow and red for both the homes and the businesses. That's kind of a metaphor here, right? We don't know whether the color of the house influences the use of glass cleaner more, right? People in yellow houses use more glass cleaner than people in red. But this could be a metaphor for a lot of things, right? I use color, house color is a pretty innocuous thing here, but it could be pretty much any measurable population pattern here, right? So assign what other variable you want to that. Think of the red and the yellow as metaphors, right? So we've got this difference going on here. We think it might influence the gas cleaner usage. We don't know. We don't know really ahead of time if businesses use more or less than residences. So we've got a couple different things going on here, right, within this example setup. So in a randomized control trial, what we'd want to do is randomly divide the entire population, right, all our possible customers up into what we call a test group, where we're going to send them, in this case, the email. So the test is the impact of email, and a control group. And the control group is going to get the direct mail ad. So if we do a randomized control trial, we're literally flipping a coin or using a computer random number generator to assign customers into one of two categories, right? Just split them up at random, so it should be blind to where the house is located, whether it's a business, what color it had, everything, right? If we use a random control system and we have a large enough data set, we're going to get two comparable groups, right? The only difference between them is this kind of random flip here. And so if we've done it right and designed that well, we get this kind of even split. You might have to, so I have a question here. Ideally, the groups are evenly split. What about when the data is then excluded? Yeah, so if you have to have exclusions, right, which is going to be common in advertising because not all your customers are going to allow that, you may want to do something like a random draw of the customers that are allowing the advertising, right, some usage. And there are other ways of thinking about how to handle that. But there are tactics that are called stratified sampling to make sure you have a good representative set. So there's a whole set of technologies for that. But ideally, what you're trying to do here is wind up with a testing control group that's apples to apples, right? Not apples to oranges. And you do that by these randomized control designs. And there are different ways of doing that. The simple one here is just to randomly subdivide. Again, if you needed to do a stratified sampling to make sure you had the right proportion of businesses and the right proportion of residential homes in the sample, there are known ways of doing that. It's been worked out in the statistical literature. So if we have an ideal design like this, right, we'd be looking at what's called the causal impact of the email. And so the causal impact would be the sales in the area to customers with the email ads and sales in areas with direct mail. So if we're able to, if we're dividing this out by small geographic area, we might look at the sales in that area. If we can track individual customers, that's even better because then we can really look pretty closely at what that effect is. So causal impact is just the effect we're looking for, right? We would hypothesize that the email ads did worse, right? Maybe. Well, the note I've got here is saying if the email ads did better, then we would have a positive causal impact. If the email ads were worse, we would have a negative causal impact. So when I mentioned the Volkswagen example we're going to look at in a few minutes, we would think it's a negative causal impact, right? That this EPA penalty applied to Volkswagen, along with the idea that their diesel cars were essentially fraudulent in terms of their emissions profiles, caused negative impacts on VW stock, right? So the causal impact there we'd expect to be negative. So if we had a randomized trial, right, then we've got apples to apples comparison, and we can just go ahead and look at the responses in the two groups and get a pretty good estimate of what the impact of the treatment was. But the randomized control trial requires this intervention, right? We've got to randomly assign by a coin flip or random number generator to assign individuals to the groups, right? So we've got to intervene, right? We're making an action in the world where we're an actor, we're making a choice. The randomized control trials are a gold standard. It's the best way to control for unknown factors, right? I mean, we may not know what the color of the house is even, right? But they do require this intervention. So in many cases, intervention might be impossible, right? If we're studying a unique event or a natural disaster, we can't cause that, right? The VW admissions scandal is not something we can control, right? We can't say, well, we'll look at VW and GM and we'll force one of them to have an emissions scandal, right? You know, it's not going to happen. Intervention might be unethical, right? Treatment might cause hardship to people, right? You can't expose people to COVID deliberately or coronavirus. A bunch of other situations where it's just not acceptable to do that, and we're trying to work from observational data or recordings. We might have a lot of information about consumer behavior, you know, from tracking our orders or from interactions with websites or other types of information that wasn't really designed as an experiment initially, but we have a long record of our business activity. We want to figure out how do we make use of that and try to understand what's happening in the data and answer some questions we hadn't thought of before. And that's often the case, right? So this is about, in part, turning all those data sources into something you can drive value out of. So with observational data, we might have a situation that looks like this, right? Suppose our Pittsburgh office went ahead with an email campaign and Buffalo went with direct mail, right? So we just had that kind of random split. Could we then compare the two markets to see if the email works better? Well, this is a little cartoon here, but if you look at this, they're imbalanced, right? We've got differences in color, we've got differences in composition between the businesses, the little storefront icons, and the homes, right? So we've got this variation going on here that's not a design, there was no control on it, it just happened. Can we still make use of that? So what we have here is what's called selection bias or selection for cause, right? They were not selected in a randomized control way. They were selected in a way that that biased this, right? This happens in some cases where there's some sort of intervention, a social intervention, like a jobs training program that may have gone to people who felt that they needed jobs training strongly, right? So there's a reason for doing it. And so that's a selection bias. And so what can we do with this, right? Is there a way to handle this? So this is not an apples to apples comparison. This is an apples to oranges situation, right? Where we don't have truly comparable groups. Well, is there anything we can do with this? Again, when I start to talk about this, we have said that randomized control trial done well and with good sampling qualities is the gold standard, and it is the best. But there are some other ways to dig into this and think about how we can use that observational data to still do some hypothesis testing. And so what we're going to be doing here is looking at the following idea. We're after a causal impact again, and that's the observed result with the treatment minus what we call the counterfactual. And so the counterfactual is an estimate of what would have happened to that individual if you did not treat them. So in other words, if the household got email, right, what would that impact have been relative to direct mail for that household? Can we get any kind of prediction of that? Can we use all the data we have to try to estimate that? So when we did the randomized control trial, we could use the control group as a way of looking at what's happening here. Okay, so we had a question here. So how does causal impact and correlation differ? Correlation doesn't imply causation, right? There's no statement that one thing caused another. There's just a statement that they're paired. And so this is a step beyond that in saying, we think this ad campaign caused something to happen, right? So we're attributing a cause here. A cause is actually a human hypothesis. A correlation is a mathematical statement. So again, maybe we'll talk more about that offline at some point, or some of the ideas may be a little clearer here as I go on. So what we're after here is this estimate of the counterfactual. That's why when we did the randomized control trial, we wanted an apples to apples comparison so that the two groups were equal except for the treatment. And so the control group serves to allow us to estimate the counterfactual, what happened as a result of the treatment. So when we think about this, are the Buffalo results of these ads a good counterfactual for Pittsburgh? Well, in that example I showed you a moment ago, let's go back and look at that for a moment. Is what's happening in Buffalo a good control for the tests that we run in Pittsburgh? We've got a selection bias, right? These are not equal groups, right? There's a difference in the number of commercial versus residential, and there's a difference in the number of paint colors in the two groups, right? So these are not really comparable groups. It's not a good test situation here. So what can we do with this? So this comes into the idea of estimating counterfactuals. This has been there's been some of this going on since, actually dating all the way back into the 1940s, but a lot of discussion of this in the kind of post-big data era, post late 90s, okay? We started to talk about this. We started to see a lot of these ideas starting to come into play. So there are a series of ways of doing this. I'll mention about 3 of them. There's another half a dozen or so. If you're interested in references on this, send me some information. So we are assuming here that we've got some kind of additional data for the test, right? And we'll talk about that depending on how much data you have available. So in this picture, we're imagining we know whether it's a residence or a home, and we know what the paint color was. So we're assuming we know some things. With a lot of these processes, the more you know or the more you understand about your customer base, the better you can do with these systems. And we'll sort of see that when we look at the Volkswagen example. We'll see a little bit of that, of making use of some other data in the world to improve the ability to estimate these counterfactuals. So we'll see a little bit of that. So what are some of the tactics? Well, there are a number of approaches that get used. We'll mention a couple of them here. One idea is called differences in differences, also called a first difference method. So if we were trying to compare Buffalo and Pittsburgh, if we compare the two of them directly, we know we've got apples to oranges, and it's just not going to be a fair comparison. But one thing we might be able to do is if we had the previous year's data, right? So if we knew what the sales were like in both markets before the ad, right? We could compare the current situation in Pittsburgh to last year in Pittsburgh, and the current situation in Buffalo to last year in Buffalo, and then see which of them had a greater increase, right? So instead of working with the raw numbers, we're going to look at a shift from prior conditions, and that's called the differences in differences, because we're taking a difference from one year to another and then taking the difference between the two markets. And that's at least one tactic, and that's a little better, right? It's not ideal, but it's better. That's a straightforward enough calculation to make. The APT test and learn system uses what's called subject matching. This is talked about by a guy named Donald Rubin. He's the academic researcher who worked on this a lot. And this is a set of tactics for doing a matching process where what you try to do is find equivalent households or equivalent businesses in the two different markets and match them and look at the differences in these sort of pairwise approach to looking at things. I won't go into a lot of that today, but there's some cool technology going on there. The last thing we'll talk about is what's called synthetic control models, and that's what's happening in Google's Causal Impact tools and in Facebook's Profit tools. And so I'll show you in real time what that looks like. Basically, we're going to build mathematical models of the behavior and then use those models to estimate the counterfactual. So we're going to build not necessarily a regression model, but one type of some form of model to estimate what would have happened if we hadn't applied the ad campaign or we hadn't applied a treatment, and see what the impact was based on that counterfactual. That sounds fairly abstract. I'll show you a couple examples of what this looks like in a moment. So this idea of synthetic controls. We just had a question out. The estimate in the synthetic control model is akin to a simulation. Yeah, it's a form of simulation or a form of modeling of the response. So if we thought about this system in the Pittsburgh-Buffalo system, what we have is this. Presumably we have a prior sales history in Pittsburgh. So we've got this background information, and then we've got kind of a future sales, right? After the ad, we see the response to it by monitoring that. So what we're going to do is this. We're going to take that previous Pittsburgh sales history, the past information, and I'm presuming we have some other things. We have, say, a Buffalo sales history, right? We know what was happening in Buffalo prior to the intervention. Maybe we have some national trends. We have some idea about the factors that influence our business on a national scale. So what we have is some sort of time series information at a national level that's going to be helpful to us, right? Maybe the glass sales track the Dow Jones, right? We find out, we know when the Dow Jones is up, everybody's cleaning their windows. If the market goes down, people start economizing and they don't clean their windows. You know, that's something that has to come from a line of business. So this bit about what national trends are important here is something you have to know from an understanding of your business. So this is matching both the business sense and some of the mathematics here. And maybe we do something like we include some information about the weather, right? Because the weather probably influences how much glass cleaner people are using. So we might have a weather trend. Whatever was important to our market, whatever we think was critical there, if we can find some sort of proxy data, right, that influences that, we can include it. So we take the sales history from Pittsburgh, we take the history from Buffalo, we take sort of national trends, we take weather trends, we feed that all in and we create a model, right? Using data from before the ad campaign. And so we build our model, we test our model based on the data prior to the ad campaign, and then we look at what actually happened in Pittsburgh. So the solid purple line here is what happened in Pittsburgh, and the dashed line is the result from our model, right? And so we say, well, we know what our model performance is like prior to the ad campaign, and so we'll use it to estimate what would have happened in Pittsburgh if they'd stuck with the same ad campaign. If they hadn't shifted their campaign, what would have happened? And so the difference between them is then the causal impact, right? And so that's the idea behind this. And there are a lot of ways of building these types of models, a lot of technologies you can use here. So what I'm going to do is go ahead and show you some of this with the VW emissions scandal. So you probably remember this. I don't know if this is familiar to a lot of people, but Volkswagen had built into the engine control computers on their diesel engines a bit of software that would detect when the car was being tested in an EPA lab. So the EPA emissions tests are pretty stereotyped. They do very specific things with the vehicle. And the onboard computer in the Volkswagen could detect that, and it would deliberately alter the engine performance to reduce diesel emissions. And then when it was on the road, it would alter its behavior again to get better fuel economy and better power out of the diesel engine at the expense of higher emissions. There was some suspicion about this. I think there was a European tester in one of the Nordic countries, I don't remember where, who sort of raised the issue a little bit about that they seemed to be behaving a little oddly. And then there was some American test group that actually instrumented a couple of Volkswagens, and they drove them around the US, drove them some long distances with monitoring equipment attached to them, and they found out that their emissions indeed were a lot higher than what the EPA was reporting. And then the EPA dug into this a little bit. So there was an EPA fine levied in September of 2015, but in fact there was evidence well before that, probably about a year prior, that something funny was going on with Volkswagen diesel engines. And so you can actually see here that the solid line is the date of the EPA fine announcement. But prior to that, there was some drops and alterations in VW stock because people knew there was something kind of wrong with their engines, and maybe there's some suspicion that that's what's going to happen, that they're going to wind up with a penalty. So you can really see this drop in the VW stock price after the penalty was levied. Also on here, there are two other stocks shown. One is BMW, right? It's another German automaker. And so you'd think, well, all things being equal, that, that predicts something about the German car market, right? Exports and manufacture cars in Germany. BMW probably reflects a lot of the similar factors that are influencing Volkswagen, right? Also on here is a German financial firm called Allianz. They are a financial services and insurance firm. They are about the same size as Volkswagen. The headquarters is in the same city as Volkswagen. So they are a little less economically tied to VW than BMW is, but they're reflecting some things about the German economy in general. And so these are going to be useful. These two lines are going to be used as predictors eventually, because they're telling us something about what the general behavior was in the German stock market. So in this case, we have an event, right? The EPA announcement, and we obviously can't do any kind of randomized control on this, right? You can't, no way to do that. This is a singular event. And we're interested in the following question. What's the causal impact of this, right? What was the change in the VW stock price after the EPA announcement? And the counterfactual is, well, what would the VW stock price have been absent the penalty, right? So we're trying to estimate that. It's not something we can know. And so to do this, we're going to use an R package. R is a statistical language package. There's a package in there called Causal Impact by a guy named Kay Broder and his collaborators who are out of Google. They're using a system called a Bayesian structural time series model. This is an extension of an ARIMA time series model that if you're in financial markets, you may have seen, may have heard of. These are ARIMA models, are a pretty standard way of looking at time series models. The Bayesian time series has some advantages. It tends to be very good at trading off precision and bias. So it's, in other words, it tends to choose the right level of complexity in the models, right? It's neither too simple a model nor too complicated much of the time. So it has nice properties. So when we do this, and we just look at using the VW stock price, we can build a predictive model using the VW data prior to the EPA fine. So if you look at the left-hand side, this top image here is the VW stock price in euros. The dashed line is the onset of the EPA penalty. The blue line that you see here is this Bayesian estimator. The band around the blue line is the confidence interval, right? So we can make a statement about what the performance level of that prediction is, right? So we've got a way of saying how good is it? This is an ARIMA type model, right? This is a moving time average model of stock prices. And if you look at that confidence interval at the right side of the screen, you notice it fans out quite rapidly, right? So we get much larger here as time goes on. And that's a feature of ARIMA models. They tend to lose power over time. If you look at the ARIMA model prior to the stock price, prior to the EPA event, the blue band here is really nicely enclosing the VW stock price. So this is a pretty decent quality ARIMA model. So we have some sense of thinking, and we can test this, right? We can adjust the model. We can do some fine tuning, but this is what the default parameters gave us. It's actually a pretty decent model. This dashed blue line is the counterfactual estimate, right? That's what the ARIMA model says the stock price would have done after the announcement. So it shows some fluctuation, shows some motion there, but that's what the ARIMA model thought would happen. The dashed line here is what the stock price actually did. And so if you look at that, you can see that particularly right after the announcement, the stock price moves out of the range of the ARIMA model, right? So the ARIMA model would say, well, this is just very unlikely to happen. And so that's the causal impact, right? That's the difference between them. The middle graph is showing the difference between the observed, the actual stock price, and that Bayesian model, right, the counterfactual. And so that's what this graph is showing. So the middle graph shows that we did pretty well, right? Prior to the EPA event, there's very little difference between the two. The model's doing a good job. And then afterwards, we see this drop, right? And so that's that causal impact estimate of the EPA fine. The bottom graph shows the cumulative effect of the fine. So that's just adding up all the net changes in stock prices over time. Notice there's kind of a cone around that, and that's that uncertainty in the model, right? The model loses certainty over time because it is an ARIMA style model. Based on those graphs, we can get a little printout like this one. And so here's what I'd like to focus on a little bit. This is the average stock price. I think it's in euros for this system. And there's the predicted stock price. So the actual was 130 euros. The prediction was 168. So there's a loss there of 38 euros on average, right, each week, a decrease of about 23% in the stock price. Along with that, if you see the numbers, there's that 95 CI. So the 95% CI is the confidence interval. That's this level of certainty we have in that value. And so the pattern is pretty wide there. Looking at this relative change in the stock price, it could have been anywhere from a minus 52% to a plus 4%, right? So there's quite a band there, right? Quite a bit of uncertainty in that ARIMA model. There's an estimate of the probability of this happening by chance, and that's around 5%. So we think this is actually a real causal impact, right? There's about a 4% or 5% chance that it wasn't, right? That this is just a fluctuation. This is just what we said, I called this an ARIMA model, right? This is a very simple model based purely on the VW stock price. And, you know, ARIMA models give you something, but the quality on them is kind of limited. So what we can do to do better than that is to use the BMW and Alliance stock prices as predictors, because we think the BMW is the German car market, Alliance is the general German economy, and so that would tell us something about allowing us to predict stock prices based on the prices of other stocks. And so that's what this model is showing us, right? We have some ARIMA elements in here, but we also have these other two predictors. And so if you notice in the pre-intervention, prior to that fine, the band is a little wider, right? This model didn't do quite as well as the ARIMA model, but it has the advantage that unlike the ARIMA model, the error doesn't grow with time. It's a pretty consistent error here. And so we get a little stronger estimate of the causal impact. The value isn't going to differ that much from what we saw in the first estimate, but the confidence intervals get narrower because we're doing a better job of predicting when we're allowed to use these proxies of other conditions in the German auto market and in the German economy as a whole. And so this is the resulting statement about causal impact. We can now say that the actual price was 130, that didn't change, but the prediction was 176 with a standard deviation of 5.9. So we're now getting a much tighter statement on exactly what that impact was. At the end, we've got a relative impact here of minus 26% that could range anywhere from minus 33 to minus 19% on that stock price. So now we've got a pretty tight interval here, right? We can make a strong claim that this was anywhere from a 19 to 33% decline in the VW stock price as a result of that penalty. So that's just illustrating a little bit about how these models are built. Any quick questions or comments here before I move on? We're going to take a look at some COVID data in a moment here, but I just want to ask if anybody has any questions on this one. If you think about them, we can talk about them at the end here. Okay. So the corona event, the pandemic. I want to give you a warning here. I'm going to talk about deaths in the corona event. You know, if that's something that bothers you, just be a little aware of it. You know, if you want to drop out at this point, we've seen one example, but I am going to go ahead and talk about more human mortality. So I'm just, you know, giving a bit of a warning here. I do this. I found out I started doing this. You know, I came out of physics, and so they really don't have to give much warning in physics, right? Not much of a problem. But I did some things in forensics, and I found out that this type of statement about warning really didn't matter, right? So. There's a nice question here, and maybe we'll let people talk about that. You know, I've looked at Johns Hopkins and Worldmeter for some of this. I'm using the data we're going to use today is from the CDC. So this is the US CDC data. One of the issues we have, and that really points it out, in the COVID pandemic era, we've got a number of problems about mortality and about estimates of COVID infections. Two things, you know, the testing is not where we'd like to see it in terms of the data quality. And the other thing is we think there are a lot of biases on different parties that to either increase or decrease the COVID diagnoses. And also with humans, most of the time when people die, they're not dying from one single cause, right? They've got a bunch of pre-existing conditions, there are a bunch of things wrong with them, and it's kind of a cascade effect, right? I mean, if you're hit by a bus, you're hit by a bus, the bus caused it. But, you know, a lot of the other cases, you know, you've got a bunch of things wrong with you, right? I mean, a lot of people die of pneumonia, but they've got a whole bunch of other conditions associated with it, right? Pneumonia is a big killer, but a lot of people who die of pneumonia have cancer or heart disease or, you know, a bunch of other things. So we've always got this comorbidity issue that's involved with it. So there's a lot going on here. In the models I'm going to show you, what I've got here is weekly counts of death by state, and there's a lot of cause information there as well. But I'm really looking only at the weekly mortality by state, and New York City is actually broken out in this data set. So we've got New York City and New York State, and that's what I'll look at. But in fact, they have this for every single state. The data set comes in two pieces. One of them is from 2014 up through the end of 2018, and that is vetted data, right? So it is formalized and approved, and the CDC is pretty sure this is really pretty correct. And then we've got data from 2019 and 2020, which runs up until June 6th, and that's what's known as provisional data. So it's subject to some further checking, but it is CDC's best statement about mortality. It has got a whole bunch of causes in it. You can go and download this if you're interested. It's a neat thing to be able to look at. But as I said here, what we're going to do is work just from the weekly mortality. So we're not going to worry about what the diagnosis was, other than somebody died, right? So hopefully in the CDC data, that idea that yes, somebody, there were this many deaths in that state that week, hopefully that's correct. Yeah, and it is very worrisome. We all know this in the current era. But that's what I have. In this, here are the observed and predicted New York City mortality. I can email the information out if you want this. If you'd like this, I can send you the whole presentation. That may be the easiest way to do this, but I can send you links. If you're really deeply interested in this, I do have, it's not in the presentation, but I do have references on some of the technology involved here. So if you're interested in that, drop me an email. I'm just sheets@canisius.edu. I'm happy to send you some references on these ideas. So again, what I've done here is I just took the observed and predicted, the observed New York City mortality. The times on here, starting at 0 and going up over 300, are the number of weeks since January of 2014. So I didn't bother to scale all this to exact dates, but it is just numbered weeks, right? This is the approximate onset of the COVID events, is this dashed line right here, a few months back, and then we can see the time moving on. So what I did was build one of these ARIMA models, just like we did for the Volkswagen stock prices, of mortality in New York City, right? So I just used all that data from 2014 up until early 2020 to build the model. And I added in this time seasonality, because if you look at this data, you can see that the data is not flat, right? It's got a little bit of rippling in it, right? And that is because of flu season and some of the other diseases that hit us in the winter. And there is higher mortality in New York City in that seasonal way. And so there is a seasonality model added into the ARIMA. So in other words, if there's a pattern in the data that corresponds to seasons, this data crops up. So what I've got going on here is, prior to the COVID event, you can see that the ARIMA model tracks that mortality dead on, right? It's very nice. I've got a fairly narrow band here, meaning fairly high confidence levels. And then in the COVID era, you can see that strong spike occurring in New York City mortality. So the difference between them is the net excess deaths in the COVID era. They may or may not be caused by COVID. We don't really know that, right? They are just in the post-COVID or the pandemic era. This is the point-wise estimate is that causal impact estimate. That's that second line. So you can sort of see we've got a big spike, right, in the COVID era. And there's the cumulative excess deaths caused by the COVID event. I should mention at this point, if you're interested in taking a look at this, there's a series of New York Times articles that extend back 3 or 4 weeks ago, where they use this type of technology. This is my own data. I ran this, but it's the New York Times articles. There's a group at the New York Times that's using exactly this technology. They cite their data sources. I'm not sure that their data all came from the CDC. Part of it came from, I think, some New York City sources. I repeated some of that for the CDC data. There is this information, by the way. It is available for all 50 states. It is an ongoing process of the CDC. So if you want to see that data, you can go and download it. Anybody can. I did this a couple nights ago. Straightforward process. Comes down as a sheet. You can load in Excel if you want to. I loaded up into a processing package called R and did it there. You could do it in a bunch of other tools. Anyway, so this is what happens. The predicted mortality in New York City per week is about 1,000 per week. 1,000 for fellow humans pass away each week. During the COVID era, that average was 2938. So we had an excess mortality there of about 1,900 people per week. So that was the departure from the background mortality in the pandemic era. It doesn't mean that COVID infections directly caused all that, right? We don't know. There are probably fewer highway accidents, for example. Maybe not, that's probably not a big deal in New York City, but in the rest of New York State, there are probably fewer highway accidents because of reduced traffic on the roads, although there may be more people speeding, so I don't know. Anyway. And this does incorporate comorbidities, right? So in other words, if you had something else wrong with you and you got COVID and you passed away, it's this total impact of the COVID event. This also reflects things like if someone has a heart attack and they don't go to the hospital because they're afraid of getting COVID, then their mortality goes up, and that would be included in this. So it's all effects of the pandemic era. The number I came up with for this on it is that during this interval, so that was the start of the pandemic, and I have to look at the exact date on that, 309 was my starting point here, up until 606, The total count of excess deaths was about 24,800. So that's above the normal expectation under the counterfactual. The CDC count, so we just took the CDC data and they've got a listing there for COVID-related deaths that the CDC lists, and that was about 18,800. So there was about a 20 or 30% excess deaths that in the COVID era that have not been diagnosed as COVID. So that's all other sources of mortality during that interval. Okay, so I think probably this indicates that there were more mortality caused by the pandemic than is being directly attributed to COVID infections. If we take a look at the same data for New York State, I pulled the New York State data. Again, there's the ARIMA model. It has the seasonality again, so this fluctuation with the seasons in here. You can see what the ARIMA model performance looks like. Then there's the onset of the COVID interval, and we can see the impact of that, you know, in the model. And then for the summary table, we're seeing typically in the rest of New York State, excluding New York City, about 1,900 mortality events per day in the pre-COVID era. The actual seen in the COVID era, about 2,800. So an excess count there you have about 12,000 deaths in the COVID era in New York State, leaving aside New York City, and then the expected CDC count of COVID of about 10,000. So again, it looks like there's more mortality here. Yeah. Yeah, what you could do with this, I mean, there are a number of things to look at this. There are some Times articles that use this technology to estimate excess deaths. There's some information on the CDC websites that look at these types of excess death models. I ran my own here, used the CDC data, and ran this in an R package. So I'm going to close there. Really, what I've hoped I can show you here is that there are ways of getting these kinds of causal impacts without having to have a randomized control trial. You do get these statements about these relative effects. You get a confidence interval, so you get a statement of not only what do I think the impact was, right? Saying that we think the impact was 926 excess deaths per week in New York State in the pandemic interval, but we could say that that range is 868 to 982. So we've got a confidence interval here that gives us a quantification of just how much we think we know about this. We got a probability of this event occurring by chance at about 0.01%, so a tenth of a, or 0.001, about a tenth of a percent chance that this was a random fluctuation. So we can make these types of statements about this type of data without having to do an explicit hypothesis testing process. Yeah. So maybe I can open that up to questions here. Yeah. We have a nice comment here about logarithmic population ideas. So there's some interesting ideas, some context here about contact tracing and self-reporting. So some good things out there. Yeah. Have I seen the WPA COVID Trump excess death counter? I haven't seen it. I haven't dug into it. I could pull the CDC data, right, or anybody could, right, and take a look at some of that and see what those numbers look like. The diagnosis, there's so many conflicting factors going on here with how deaths are attributed to COVID, right? And we've got both the right and the left claiming that the numbers are skewed. What I do see in this, and I think what a lot of the New York Times articles are saying, is that the mortality in the COVID era is higher than normal. It is about 20 to 30% higher than the deaths reported as associated with COVID. So it's 20 to 30% higher than the diagnosed cases, right? So, but again, we've got comorbidity here, right? So we've got this issue of, well, why did the person die? Was it the COVID or was it something else? And it's very hard to pull that apart. But we are seeing those kinds of excess deaths. So that finishes off. If you're interested, my email is just sheets@canisius.edu. I'm happy to send you the presentation. I'm happy to send you links to some of these types of tools. Yeah, just hopefully give you a little look today at how you can use mathematical technology coupled with big data sets to get some estimates in situations where you can't do randomized trials.
I'd like to thank Dr. Sheets again for putting on this virtual discussion and everybody for your participation. Again, the presentation will be sent out as a link to everybody who did attend today, and also will be put up on the Canisius website. So you will be receiving this. And again, if there's any other questions, you can definitely reach back out to Dr. Sheets. And thank you again for joining us for today's presentation.
Thank you all for attending. I see some familiar names on there. Appreciate you taking the time to show up today.